Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 26. In lecture number 26, we are going to discuss about the concept of composite wall, which is a multi-layered wall. Let's recollect what we have discussed in the previous lecture. We have started the heat transfer, that is module number 5, the topic heat transfer, the conduction heat transfer. So, if we have a look at the heat transfer mechanisms, there are three mechanisms: conduction, convection and radiation. Conduction and convection require a medium, whereas radiation does not require a medium. So, conduction is the transfer of heat due to the vibration of molecules, It could be from one solid to another solid or between two different regions of the same solid. And the governing law for conduction is Fourier law of heat conduction, which states that the rate of heat flow is directly proportional to the temperature gradient. Of course, the area of the wall remains constant. So, to remove the proportionality term, constant was introduced, that is called the thermal conductivity of the material, which is used to construct the object or the object or the wall or cylinder, whatever whatever we are going to focus on. So, the unit for thermal conductivity is watt per meter Kelvin. So, in one of the slides I have displayed some K values, compared the K value and specific heat capacity values of a solid, liquid and gas. I have took an example of copper and liquid water, and for the gaseous substance I have taken air. If we compare the specific heat capacity with the thermal conductivity of these substances, copper has got a thermal conductivity value of 401 watt per meter Kelvin, whereas the thermal conductivity value of water is less than 1, it is around 0.6 watt per meter Kelvin. If we compare the specific heat capacity value between the two substances, the Cp value of copper is less, whereas the Cp value of water is 4.18 kilojoule per kg Kelvin, and for copper it is around 0.4. Okay, roughly it is about 9 to 10 times less than that. So, what does it indicate is the thermal conductivity, it is the measure of the ability of the material to conduct heat. So, in this case copper has got a very good K value compared to water and air, significantly higher value, and Cp is something, it is a measure of ability of the material to store the heat, So, water has got good potential to store the heat rather than to conduct the heat. In the case of copper, it has got very high K value, but negligible Cp value. Similarly, when we take water and air, Cp value of water is 4 times, little over 4 times than that of air, and of course, K value for air also is very small. Next we have discussed about the Fourier law of heat conduction, which was applied to a cylinder. So, for a radial component Q equal to minus K dt by dr. So, for the we have to apply the substitute the surface area of the cylinder and derive the equation. Similarly, for sphere we have to apply the surface area 4 pi r square, and we derived the Fourier law of heat conduction for sphere as well. Then we have solved numerical questions based on these topics. So, now with this background, let us move to the contents of this lecture. Let me start the lecture with an introduction. Thermal resistance, the concept of thermal resistance, which is very important. Comparison between thermal and electrical resistance, multi-layer plane wall, and a few numerical questions based on this composite wall. So, if we see the basic equation, the Fourier law of heat conduction for a plane wall, Q equal to minus Ka dt by dx. In this area is the heat transfer area, dt by dx is the temperature gradient. As we move along the positive x direction, how does the temperature change, that is change in temperature with respect to the location. At the extreme end of the wall, say x is equal to 0, here dx is nothing but L in plane wall. Let me emphasize it again, dx is equal to L, which refers to the thickness of the wall. It is not the length of the wall, it refers to the thickness of the wall. So, in we can use the term dx or L also, capital L. Now, this negative sign indicates the heat flow is in the positive direction. So, when we write T2 minus T1, because heat is being transferred from the hot region T1 to the cold region T2. So, T1 is greater than T2. So, when we write the change in temperature, that is T2 minus T1, so we get a negative sign, and of course, heat cannot flow from negative to from a colder region to a hotter region. So, a negative sign has been introduced to indicate that the heat flow is in the positive x direction. So, the equation becomes Q equal to, instead of minus Ka T2 minus T1 by L, it becomes Ka into T1 minus T2 divided by the thickness of the wall, where K is the thermal conductivity of the wall material. Now, what is the need to go for a composite wall or a multi-layered wall? So, if you see, determining the rate of heat transfer under steady state conditions, it is of very importance. When we say steady state condition, that the property does not change with time with respect to it, that means the system has attained a steady state. So, there is no change in the property of in the system, like assuming Q value to be constant. So, in such conditions, the rate of energy, the rate of heat transfer can be easily calculated, in the sense like by applying the concept of thermal resistance, which is another way of calculating the rate of heat flow either through a cylinder or a sphere or through a plane wall. So, the concept of thermal resistance can be easily used for to solve such type of problems in heat transfer. Let's see what is this thermal resistance. So, this is a plane wall which I have discussed already, which you have seen in the previous lecture also. This is the thickness of the wall. This is the thickness of the wall thickness. The heat flow is from the positive x direction. So, at this point, thickness of the wall is equal to 0, and at this point thickness of the wall equal to capital L or dx. Suppose if the thickness of the wall is 20 millimeter, that is 2 centimeter. So, here it will be 0, here it will be 20 centimeter, and we can find the temperature at any location on the wall between 0 and L, between 0 and L. So, the heat flow is from 1 to 2, that is T1 to T2. So, this we have already seen. So, Ka, so I have multiplied by the minus sign. So, K into A into T1 minus T2 divided by L. Okay. So, that is minus Ka dt by dx, dt is T2 minus T1. So, minus sign is there, minus of minus will become plus. So, T1 minus T2. Here I am bringing this term to the denominator. Okay. So, bringing this term to the denominator. So, it is L by Ka. So, numerator there is only one term, that is change in temperature, delta T, T1 minus T2. So, the denominator term is called the wall resistance or the thermal resistance of the wall. Okay, that is L by Ka. This is R suffix wall is equal to L by Ka. It is only applicable for a plane wall, not for a cylinder or not for a sphere or any other configuration. So, where R suffix wall is the thermal resistance of the wall. This is nothing but the conduction resistance, that is the resistance offered to the flow of heat, If you take the cylinder, okay, so let us, this is the thermal resistance for a plane wall. Let us write the equation for cylinder. Q equal to 2 pi KL T1 minus T2 divided by ln of R2 by R1. So, this is the equation which we derived by applying Fourier law of heat conduction. So, bring this 2 pi KL term to the denominator. So, what happens is, so this is equal to T1 minus T2 divided by ln of R2 by R1 the whole divided by 2 pi KL. So, this is the term which is in the denominator. So, this is nothing but T1 minus T2 is nothing but delta T divided by resistance of the cylinder, where the cylinder is equal to ln of R2 by R1 divided by 2 pi KL. So, this is the thermal resistance of the cylinder. So, what if I suppose if I know the rate of heat flow, if I know the rate of heat flow, okay. So, if I know the rate of heat flow, if Q is known, okay. If I know the thermal resistance value, then I can find delta T. Delta T equal to Q into thermal resistance of that particular configuration. Okay. So, therefore, delta T is equal to, in case if delta T is unknown, so we can multiply Q into thermal resistance of the cylinder. So, this similarly for a plane wall, delta T equal to heat flow, the rate of heat flow into the thermal resistance of the plane wall. So, this is for a cylinder, this is for a cylinder. Next, let us find the thermal resistance of a sphere, So, 4 pi K R1 R2 into T1 minus T2 divided by outer radius minus inner radius. So, this is this is the equation which we derived for a heat flow through sphere by applying the Fourier law of heat conduction. So, this is equal to T1 minus T2. We have to keep the term temperature difference in the numerator and bring the other terms to the denominator So, that is R2 minus R1 divided by 4 pi K R1 into R2. So, this is nothing but delta T divided by thermal resistance of the sphere, where R of sphere is equal to R2 minus R1 divided by 4 pi K R1 into R2. So, here also if we know the temperature difference, suppose if we know the rate of heat flow and the thermal resistance of the sphere, we can find the delta T. Or if we know the temperature difference and rate of heat flow, we can find the thermal resistance of the sphere. Suppose, so R of sphere is equal to delta T by Q. Okay. So, here I have given the detailed this one for a plane wall, for a cylinder and sphere. Okay. So, I have explained just now. So, this is the conduction resistance or the thermal resistance for a wall, cylinder and sphere. Suppose if you take, there are more layers in a plane wall. Suppose there is a wall like this. Anyway, I am going to explain about this one with the schematic. Let us take a composite wall. A composite wall is a multi-layered wall. So, let me explain. Before seeing the composite wall, let us compare the thermal resistance with the electrical resistance. It is similar to the electrical resistance. Okay. So, here if you see, the driving force for heat transfer is delta T, temperature difference, T1, T2. The driving force for the current flow is potential difference, that is voltage V1 and V2. So, instead of T1 we are having V1 in electrical analogy, instead of T2 we are having V2. Okay. So, this is V2. So, here this should be V2. Okay. So, this should be V2. Okay. This is not V1, this should be. So, here the rate of heat flow can be found, it is the ratio of delta T to the resistance of that configuration. So, that is R. Okay. So, here the resistance is for a wall, it is L by Ka, for a wall it is L by Ka, T1 minus T2 divided by R. The equivalent one in electrical analogy is, instead of Q we are having current flow, instead of rate of heat flow, instead of heat flow we have current flow, instead of delta T we have delta V, that is V1 minus V2 divided by, this is the thermal resistance, R represents the thermal resistance and E represents the electrical resistance, and we know the Ohm's law, V equal to I into R, V equal to I into R. So, I equal to V by V equal to I into R, I equal to V by R. Okay. So, that is how it is written. So, when we compare the thermal resistance and the electrical resistance, only there is a difference in the concept, otherwise the terms are all similar. Instead of delta T temperature difference we have potential difference, instead of thermal resistance we are having electrical resistance. Multi-layer plane wall. So, the plane wall consists of, multi-layer means more than one layer. Okay. So, when we say plane wall, it consists of only one layer of a particular thickness. Okay. So, when you can say composite wall is nothing but a multi-layered plane wall, adding more layers to the plane wall. Okay. So, it can be added in parallel, can be added in series also, we will see. So, plane wall consisting of several layers of materials. It is also known as composite wall. It is also known as composite wall. So, the thermal resistance concept is used to determine the rate of heat flow under steady state conditions. There is one limitation when we apply this thermal resistance. So, as long as the flow, the heat transfer is in steady state, so we can use this one. In case if Q is changing, so then this concept cannot be used. So, that is one limitation, that is the main limitation of employing thermal resistance concept. So, once we know the resistance of the individual wall in the composite wall, in the composite layer, so the summation of the individual resistance of the wall will give the total resistance, Okay. So, here I have taken one example, a wall which consists of two layers, like we can say layer 1 or layer 2, layer 1, layer 2 or wall 1 and wall 2. The wall 1 has a thickness of L1 and it has a thickness of L2. Thermal conductivity of the wall, first wall is K1 and that of the second wall is K2. Okay. So, the rate of heat flow is in this direction. So, here we are considering both conduction as well as convection. So, the heat transfer coefficient due to the convection is HA on this side, temperature is TA, okay, ambient condition, this one, and here it is HB and T suffix B. These are all the temperatures. The interface temperature between wall 1 and wall 2, it is this point, this is the interface temperature T2. Both the wall 1 and 2 are joined together, okay, Okay. So, theoretically we assume there is there is a perfect contact between the layer 1 and layer 2. There are no gaps, but in actual situation sometimes what happens is there may be a slight gap between the layer 1 and layer 2, like that gap would have been filled with air. Though air has got a low thermal conductivity value, it will offer some resistance to the heat flow. So, when these multi-layered walls are constructed, we should care should be taken that there are no air gaps at the point of interface. Now, there are here outside the wall this is rate of the heat flow is due to the conduction into the wall, then conduction is within the wall. Okay. So, here on the left side it is convection CONVECTION into the wall, then the heat flow between the layers of the wall is conduction, and the layer which is and the region outside this one is the convection from the wall. This is convection into the wall, this is from the wall, and this is within the wall, So, when we write the resistance, so here I have got one resistance RA, okay, we can take R1 also, if you want we can take RA, and this resistance is RB, okay, I have taken here R4. So, we can take RA and RB also, okay. So, and the thermal resistance of the first layer of the wall can be used as R1 and this can be R2, but here because I have taken R1 in the increasing order. So, the convection, the resistance due to convection which is into the wall, that is R1, then the conduction resistance of the wall, first wall R2, conduction resistance of the second wall R3, and the convection from the wall, the resistance due to convection from the wall is R4. So, this equation we will be seeing in the next one, that is I will be explaining what is this equation. So, time being let us take one, it is 1 by HA, because there are two heat transfer coefficient, HA on the left side. So, I am writing HA into A, of course, area of the wall remains constant, and right side it is 1 by HB into A, and we know how to write the thermal resistance of a due to conduction. The thermal resistance due to conduction is L by Ka, the thickness of the wall divided by the product of thermal conductivity and its heat transfer area. Okay. So, this K value of the wall material will remain constant, area will remain constant. Okay. So, this thickness also, unless otherwise it is changed, it will not change. So, since we have two walls, L by Ka is written as L1 by K1A and L2 by K2A, Okay. So, this is the equivalent electrical resistance. Okay. So, this is how we represent the equivalent electrical resistance. This is for the R1 is for the convection into the wall, R2 and R3 are the conduction wall resistance for wall number 1 and wall number 2, or layer 1 and layer 2, and this is for convection R4. So, add all the resistance 1, 2, 3, 4. Okay. So, in this case all these things are in series, R1, R2, R3, R4. So, L1 by K1A plus L2 by K2A. So, that we get the total resistance. Once I know the total resistance, delta T is known. So, delta T by the total resistance gives the rate of heat flow. Now, let us take an example of a composite wall, okay, which has, in the example which I have explained, it is the layers are in series. Let us take a wall like this. Okay. So, this is layer 1 or wall 1, this is layer 2, this is layer 3. Let us take the thickness of this wall, okay, as L1, this is L2 and this is L3. Let us assume that the wall 1 or layer 1 is made up of thermal conductivity K1, this is K1, thermal conductivity is K2. All the three walls are made up of different layers, and this is K3. Okay. So, K1, K2, K3 are different thermal conductivities, and the corresponding thickness are L1, L2 and L3. Now, if you see, so these actually this we have to find out the equivalent resistance. If I draw the equivalent the equivalent circuit, okay, the electrical resistance. So, for this let us assume that the example which we have taken is involves only conduction, there is no convection, okay, there is no convection. So, let us take this temperature as T1 and this is the interface temperature T2 and this will be T3. Okay. So, the rate of heat flow will be like this. Okay. T1 is greater than T2 which is greater than T3 and the rate of heat flow is in this direction Q. So, now the resistance for layer 1, before that let us draw the equivalent electrical resistance. So, it is like this. So, let me draw it again. So, here we have got this is the resistance, equivalent electrical resistance corresponding to layer number 1. Then we have resistance here, okay. So, this is layer 1, this is layer 2 and this is layer 3, okay. So, this is the direction in which it is layer 3. So, that means this is R1 resistance, this is R2, this is R3 and R3. So, these two are in parallel, layer 2 and layer 3 are in this one parallel. So, here we can find out R1 L1 by K1 into A, area remains constant, okay. So, we can find out the equivalent resistance, So, because 2 and 3 are in parallel, so equivalent resistance is like 1 by R2 plus 1 by R3. So, if it is in series, we know we can add it directly. If it is parallel, we take this one. Okay. So, 1 by R is equal to so if you take LCM R2 R3, this will become R2 plus R3 which is equal to 1 by R. So, therefore, let us take this equivalent resistance only for these two, layer 2 and layer 3. So, therefore, R equivalent is equal to R2 R3 divided by R2 plus R3. Now, once I take the equivalent resistance, it becomes a series connection with the layer 1 and we can add R1 and R equivalent will give this one. So, R total is equal to R1 plus R equivalent. And how to find R2 and R3? That is, if you consider layer 2 as a single plane wall, L2 by K2 into A and R3 will be equal to L3 divided by K3 into A. That is, R2 is the thickness of the second layer divided by its thermal conductivity and multiplied by the area. And similarly, resistance at layer 3 is thickness of layer 3 divided by K3 into A. So, once I know R2 and R3, substitute in this one, find out the equivalent resistance. So, this will become, once I take the equivalent resistance, this will become like this. Okay. So, this will become like this. So, this is R1, this is the equivalent resistance and equivalent resistance is this one, equivalent resistance is this one. So, this is how we have to find out, and the total resistance. Once we know the total resistance, Q is equal to delta T by R total, So, this is in case of series and parallel configuration. So, with this background, let us solve some numerical. Okay. Heat transfer through a composite wall is shown in figure. So, the problems, numerical questions which we will be solving it will be pertaining to the composite layer, multi-layered wall. Okay. The conductivity of one section is K and that of the other is 2K. So, thermal conductivity of the first layer is K and that of the second one is twice the value of the first layer. The left face of the wall is at 600 Kelvin and the right face is at 300 Kelvin. Determine the interface temperature of the composite wall. So, I have converted the given schematic, given data into form of schematic. So, the rate of heat flow is in the positive x direction. On the left face, it is given as temperature is 600. Okay. The left face of the wall is at 600. Okay. The left face of the wall is at 600 and the right face is at 300. Okay. So, this is wall 1, wall 2. So, let us say the thickness of the wall is we have taken L, assuming it is of equal thickness. This is the intermediate temperature which we have to find out. This is the intermediate temperature which we have to find out. Okay. And it is clearly given K value of the first wall is, if it is K, the K value of the second wall is twice that of the first one. So, K 2K. Okay. So, here it is given. Let us take this as T1, left face temperature. Okay. Left face temperature and let us take T2 is 300. So, obviously, heat flow is from T1 to T2. Okay. T1 is greater than T2. This is right face temperature. Okay. Now, the layer 1 is given, we have to find out the intermediate temperature. We have to find out, temperature at the point of contact where both the walls are joined. Okay. So, we have to find this one. So, okay, we are going to apply the Fourier law of heat conduction, the derived equation, that is Q equal to Ka T1 minus T2 divided by L, okay, or the thermal delta T divided by L by Ka, which is the thermal resistance of the wall. Okay. So, for steady state heat transfer, the heat flow, because we assume the condition to be steady state, heat flow through the wall 1 will be equal to the amount of heat flow which is flowing into the wall number 2. Okay. So, here it is like this, the wall is like this, this is the wall 1, this is wall 2, this is T1 equal to 600 Kelvin, this is T2 is equal to 300 Kelvin, this is the intermediate temperature which we have to find out. Okay, which we have to find out. So, the heat is flowing in this direction. So, it is from T1 to Ti for the first wall, and for the second wall it is from T1 to Ty, it is from T1 to Ti, first wall 1, and for the second wall it is from Ti to T2. That is how Q is flowing. Okay, that is how Q is flowing. This is for wall number 2. So, write the equation for this one. So, we will write directly the Q equal to Ka delta T by L. Okay. So, this is, we know that Q is equal to Ka delta T divided by L. Okay, we know that. Now, the under steady state condition, under steady state, the rate of heat flow in wall number 1 due to conduction is equal to rate of heat flow in wall number 2.
So, therefore, instead of K I will write K1 into A, temperature difference is T1 to Ti, T1 to Ti. Okay. So, this is for wall number 1, T1 to Ti, this is for wall number 2. So, this is equal to T1 minus Ti divided by, okay, length of the wall, since it is not mentioned, it is clearly given equal thickness. Thickness of both the walls are same. So, that means it should be L. Okay. So, this is L and this is also L, equal thickness, wall of equal thickness. So, divided by L, this is for the first one, this is for the first one, and for the second wall the heat flow is from intermediate temperature, which we have to determine to point number 2, T2. So, that will be Ka, that will be K2A, okay, K2A into Ti minus T2. For the wall number 2, it is from Ti to T2 divided by L. Now, K2, see let us take K1 is equal to K1 and K2 is equal to 2 times K1, it is clearly given. So, this is K1, this is K2. So, this is the thermal conductivity of the wall number 1 and this is the thermal. 2I is that of the first layer thermal conductivity. So, instead of K2 I can write K1, 2 K1. So, therefore, K1 into A the T1 minus Ti divided by L is equal to, let us we will do one thing, we will take the value which is given in the problem. K1 is equal to K and K2 is equal to 2 times K1, therefore, K2 is equal to 2K. So, let me write that value. Okay. This is K and 2K. So, this K1 will become K equal to, K2 is 2 times K, K2 is 2 times K. So, 2 into K into area into T8 minus T2 divided by L. Okay. So, A term, L term will get cancelled, K 1K will get cancelled. If you simplify, and this one is given, T1 is given, T2 is given. So, the only unknown is Ti. If you substitute the value and simplify, you will get Ti as 400 Kelvin. So, Ti will be lying between, T1 will be greater than Ti, but and Ti will be greater than T2. Okay. So, we are getting in between, it will be interface temperature will be less than T1 and greater than T2. So, that is the answer, 400 Kelvin. Now, let us move to the second one. Consider a 0.8 meter height and 1.5 meter wide glass window whose thickness is given 8 mm and thermal conductivity is 0.78 watt per meter Kelvin. Determine the steady rate of heat transfer through this glass window and the temperature of its inner surface for a day during which the room is maintained at 20 degrees centigrade, while the temperature on the outdoor is minus 10. So, the temperatures are given 20 and minus 10. The heat transfer coefficient due to convection on the inner and outer surface of the window are 10 watt per meter square degree centigrade and 40 watts per meter square degree centigrade respectively. Okay. So, the conditions are given 20 and minus 10. The thickness of the glass window is 8 mm, okay, 8 mm, and HA value is also given, HB value is also given, T1 and T2. Okay. So, let us write the given data. Thickness of the window is given 8 millimeter. So, that is equal to 0.008 meter. Area is given, okay, 0.8 meter into 1.5. Okay. So, 0.8 meter into 1.5 meter. So, multiply, you will get 1.2 meter square, 1.2 meter square. Okay. K value of the glass is given, K is equal to 0.78 watt per meter Kelvin. heat transfer coefficient value is given 10 watt per meter square degree centigrade and the HB value is 40 watt per meter square degree centigrade. Here I would like to emphasize one point. So, when we write the K value and H value, since because it is for temperature difference, so you can write in the instead of degree centigrade you can write Kelvin also, watt per meter degree centigrade, which is the unit for K value, SI unit for K value. The same value can be written as watt per meter Kelvin also. No, there will not be any change in the value, that is because that is temperature, that is due to the temperature difference delta T. Okay. So, now if you take this wall, okay, if you take this wall where this heat flow is like this, okay, the heat flow is like this, the temperatures are 20 and minus 10. So, from T1 to T2, T1 to T2 heat flow is in this direction. So, this is the direction of, okay. So, here you have, this is the thickness of the wall, this is the thickness of the glass, here it is a glass window. So, this is L1, okay, we can take L also or L, that is because there is only one layer. So, let us take L, let us take L and K value of this glass is given, K value of this glass is given. So, here this will be, if I draw the equivalent electrical resistance, it will be like this. So, this will be equivalent resistance. This is the conduction resistance R1 and this is the resistance due to convection. There are two convections, one is TA is given and TB is minus 10 degree centigrade, TA is equal to 20 degree centigrade, HA value is given and here also HB value is given. This is 10 watt per meter square Kelvin degree centigrade. Okay. So, here this is for convection resistance and this is a convection resistance. So, it is very easy. So, how to find RA? RA is the thermal resistance due to convection, convection rate heat flow due to convection into the wall. This is convection into the wall, this is convection and here it is conduction and again here it is convection. So, conduction within the wall, then convection from the wall, before the left side is the convection into the wall. So, the formula is we should not use L by Ka, that is used only for conduction. So, 1 by HA, because there are two heat transfer coefficient. So, this is nothing but 1 by HA into A and all these things are in series. So, whenever it is in series we have to just find add the resistance and this one. Only when you have parallel we have to apply that formula. Okay, find out the equivalent resistance and add that with the other series resistance. Now, R1 can be found by L by Ka, L by Ka. So, this is conduction resistance, these two are convection. Okay, so, this is convection, this is conduction, again this is convection, two convection and RB will be equal to 1 by HB into A. All the values are given. Okay, so, all the A value, HA, HB are given. Then you can find out R total equal to RA plus R1 plus R2. We can take this as R1, this is R2, this is R3 also. So, it is easy, it will not be confusing if you take the convection resistance RA and RB. The resistance corresponding to HA is RA and the convection, the resistance due to convection HB we will take it as RB. So, that we will use 1, 2, 3 for layers, different layers, for different layers depending upon the number of layers. So, this is R total. Now, Q is equal to delta T by R total. Okay. So, the total resistance due to conduction and convection is 0.11 degree centigrade by watts. degree centigrade by watts. Okay. So, that comes to 0.26 kilowatt, 266 watts. Now, we can find out the temperature at the inner layer. We can find out the temperature at the inner layer. Okay. So, the delta T is given. So, here delta T is 20 minus of minus 10 divided by R total. R total, let us substitute the value 0.1127, 0.1127. Okay, 20. Okay, so you will get 266 watts. 266 watts. Now, how to find out the inner surface temperature? Apply the Fourier law of heat conduction to the first, to this layer. Okay. So, that is from here to here, from here to here, Ta to T1. So, use this formula, Q is equal to, let me write it here, Q equal to, okay, Ta minus T1 divided by Ra. Okay. So, Ta by R, K into A into Ta minus T1 divided by L. L by K is thermal resistance. So, this is nothing but Ta minus T1 divided by R1, divided by R1. Sorry, this is divided by Ra, divided by Ra, because this is due to convection. Okay. This is due to, we have to find out this temperature at this point. Here Ta is also given 20 degree centigrade and Tb is equal to minus 10 degree centigrade. So, we have to find out Q value, which, that is question number 1, which we have found out, and inner surface temperature is T1, outer surface temperature is T2. So, T1 we have to find out. So, the heat is flowing from Ta to T1, Ta to T1. Okay. So, at this point, so we find out the resistance, and that value, the temperature comes to around, okay, that temperature comes to around minus 2 degree centigrade. So, if we solve this value, T1 is equal to minus 2.2 degree centigrade. It is from Ta to T1. So, that is convection into the wall, convection into the wall. So, that resistance only we have to put it, that resistance only we have to put it. Okay. So, here let me explain it again, because there is, let me explain this part again. So, to find out T1, to find out T1, see, we can, there are 3 terms are there. One is convection on the left side, then conduction, then the convection on the right side. Suppose if I take this conduction, conduction 1, it the formula in which I wrote, that is for conduction, that is for finding either T1 or T2 if either any one of the temperatures are given, if any one of the temperature is given. But we do not know T1 and we do not know T2, we know only Ta and Tb. So, I have to use the terms which is in which the heat is flowing from Ta to T1, Ta to T1. Okay. So, let me write it here, to find T1. This is the inner surface temperature. So, the heat is, heat flow is from Ta to T1, we know the value of Ta. So, Q is equal to, and from Ta to T1 it is convection into the wall, not conduction, convection into the wall. So, the delta T divided by the convection into the wall, which we have taken it as Ra, we have taken it as Ra. So, by Ra, and what is delta T? Delta T is Ta minus T1 divided by Ra. Now, we have found this value Q, we have found this Ta is given, Ra we have found. So, we can find T1 minus 2.2 degree centigrade. Suppose if you use this formula, suppose if you use this formula, Q equal to delta T by R1. R1 is the conduction resistance of the wall, not the convection one. So, delta T will be T1 minus T2 and R1 we have found L by Ka. This formula you can use if you want to find out T2, once we find T1 from the previous formula. Let me correct it, let me emphasize it again. Okay. So, this formula Q equal delta T by R1, which is nothing but T1 minus T2, and the resistance, conduction wall resistance, we can use very well use L by Ka. If we know T1, in order to find T2, if this is unknown, and this is known, if T1 is known. Okay. So, this is that completes the problem. So, here if we see the temperature that we have got at the inner surface of the glass window, of course, when I say wall, here the glass window is the wall. Okay. So, because only the configuration, configuration is different, otherwise the concept is the same. So, here we are getting a very low temperature on the inner surface. So, this is not desirable, in the sense there are chances that fog formation will be there, especially when the humidity inside the room increases. If the humidity inside the room increases, then because I am getting a temperature of negative temperature, outside temperature that this is 20 and on the other side this is 1. So, this still it is minus value. So, there are chances of fog formation when the humidity inside the room goes up. Okay. So, that completes the problem. Let us move to the third problem. Consider the problem number 2 and 3 is like a comparison. The problem which we have solved now, it is a single glass window. Now, in the next problem we are going to consider multi-layered glass in which there is an air gap and almost similar temperature, similar data, like the temperature is 20, minus 10, heat transfer coefficient 10, 40. The only thing is, instead of having 8 mm thickness, there are, so this is the glass, this is glass. So, it is a double pane window, double glass window. So, that 8 mm thickness is split into 2. The first glass has a thickness of 4 mm, the second glass has a gap, has a thickness of 4 mm, and in between the glass there is an air gap, okay, so which is a 10 mm. So, consisting of double pane window consisting of 2 4 mm thick layer of glass. So, the 8 mm thickness is divided into 2 layers of 4 mm each. K value is same, separated by a 10 mm wide stagnant air space. So, only this data is new, and of course, the thickness is half. Determine the steady rate of heat transfer through this double pane window and the temperature of its inner surface for a day, during which the room is maintenance. TA and TB are same, HA and HB are same. Okay. So, here TA is equal to 20 degrees centigrade, TB is equal to minus 10 degrees centigrade. Okay. So, thickness of layer 1, L1 is equal to 4 mm, L1 is glass, okay, L1 is glass 1, L2 is 10 mm, that is air space, and again L3 is 4 mm, glass 2. Okay. So, this is glass 1, this is glass 2, and K value for the layer 1 and 3 are same, because both are made of same glass, K1 0.78. So, the corresponding K1 is 0.78 watt per meter Kelvin, and K3 is also 0.78 watt per meter Kelvin, and for air it is given 0.026 watt per meter Kelvin. So, we can write it degree centigrade also. Okay. So, all the data are given. First find out the resistance RA 1 by HA into A, okay, there is no change. R1 L1 by K1 into A, you got this value. R2 is L2 by K2 into A. Okay. So, if I draw this one, the equivalent resistance, there are total 5 resistance. There are total 5 resistance. Let me draw this one. So, it will be like this 1, 2, 3, 4, 5. So, this is RA resistance, this is RB, these two are convection, and there are 2 glass layers and 1 air space. So, first glass layer is R1, the air space is R2 and this is R3. So, R total is equal to, all are in series connection only, RA plus R1 plus R2 plus R3 plus RB. Okay. So, RA is 1 by HA, 1 by HA into A, this will be L1 by K1A, this will be L2 by K2A, these 3 are conduction, these 3 are conduction, okay. And R3 will be L3 by K3 into A. So, let me write it, deltas are not clear, L3 by L3 by K3 into A, and RB is convection 1 by HB into A. So, add all the resistance, okay, we will get the total and apply the same formula. The heat loss, I mean there is a reduction in the, so earlier it was 266 watts, now it is close to 70 watts, and the temperature from minus 2.2 at the inner surface has increased to 14.2 because of the reduction in the Q value. Okay. So, this is a desirable one. Okay. Next, I have given 2 simple problems. So, with the solutions. So, due to time constraint, in case if time is there in the subsequent class, I will explain these 2, otherwise the detailed solutions are given. To summarize, in this lecture we have seen the concept of thermal resistance. For a plane wall, the thermal resistance is L by Ka, and similarly we can find the thermal resistance for a cylinder and a sphere based on the derived equation from Fourier law of heat conduction. So, the concept of thermal resistance is used to find out the rate of heat flow or the intermediate interface temperatures, especially for a steady state condition. For unsteady state heat transfer problems, so the concept of thermal resistance has its own limitation. So, with this let me conclude this lecture. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller. provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.